Hello and welcome to Tech Simplified TV. In last few decades, CMOS technology has gone through rapid downscaling of device dimension in order to follow Moore's law. Downscaling of device dimension has proved to be a success route and has given tremendous performance boost. Although it came up with a lot of catches. To get rid of those catch and to continue that journey, industry and academia has come up with amazing and interesting solutions. In today's episode, we will discuss about one of such solutions, that is High-K Dielectric. If you are interested, stay tuned till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. Major device milestone in VLSI, advantages of silicon dioxide, what are Low-K and High-K Dielectrics, why High-K Dielectrics, dielectric conductance and breakdown, essential qualities of High-K Dielectrics, slide 1, and essential qualities of High-K Dielectrics, slide 2. Finally, High-K metal gate structure. Now let's move to the first slide. Major device milestone in VLSI. Moore's law has been driving and guiding force for last few decades for enhancement of device performance. As we all know that for last few decades, Moore's law has been followed by scaling down device dimension to get more efficiency in device performance. To keep up with the pace of scaling, new ways found and introduced, such as device with new structure like FinFET, SOI, nanosheet FET. Second, new materials like strained silicon, High-K Dielectric, then new interconnect material like copper. So while we were following Moore's law at many steps, we had to go for new material. While doing the miniaturization, because of decreasing sizes and proximity of one device to another, proximity between interconnects, many issues arise and we try to solve them. Along with getting a better performance from the device, we have introduced new device structure like FinFET, like silicon on insulator SOI, and finally we are at a position when we are going to use nanosheet FET. We have already discussed about NSFET in one of our R&D episode. Link is provided in the description. You can watch it. We have also introduced new materials like strained silicon. Apart from mainstream normal silicon, we have gone for strained material like strained silicon and then High-K Dielectric, and interconnect material also got changed from aluminum to copper. In today's episode, basically we will concentrate on High-K Dielectric, that why we used that metal. Actually, this series we have dedicated to understand our shift or deviation from mainstream materials and device structure. Why actually we thought about new device structure or new material. In today's episode, we will only concentrate about High-K Dielectric. We also try to understand what are the requirements of High-K Dielectric and what are the problems we actually face to introduce High-K Dielectric in a stable CMOS fabrication process. So today's discussion is all about that High-K Dielectric. Like High-K metal gate, this combination has been introduced in 2010. Once we introduce new technology or new material, it doesn't mean that old one is completely scrapped. And in many applications, chips are designed on older nodes. Now, let's see. This is a diagram that's a cross section of a planar FET, and this is nano wire FET. These are basically conducting channels. There are three wires like structure, that is FET. This is the sheet portion, not the wire, a little bit wider, that is nanosheet FET. We are done with this introduction and now let's move to the next slide. Advantages of silicon dioxide. Silicon dioxide is the main reason that microelectronics uses silicon technology and not another semiconductor. It's not for silicon but for silicon dioxide because the MOS structure needs a good oxide. Otherwise, we cannot have that capacitive action on which the MOS performance is based. As a semiconductor, silicon has average performance, but in most respects, silicon dioxide is an excellent insulator. Silicon dioxide can be made from silicon simply by thermal thermal oxidation, whereas every other semiconductor like germanium, gallium arsenide, gallium nitride, silicon carbide has a poor native oxide or poor interface with its oxide. Its silicon has been chosen above many other semiconductor just because of silicon dioxide is an excellent insulator and it can be made from silicon by simply thermal oxidation. Silicon dioxide is amorphous, has very few electronic defects and forms an excellent abrupt interface with silicon. Silicon dioxide can be etched and patterned to a nanometer scale. Its only problem is that it is possible to tunnel across it when very thin. In later slides, we will understand this is the reason why we are choosing High-K Dielectrics. We are done with this slide. Now let's move to the next slide. What are Low-K and High-K Dielectrics? The dielectric constant K is parameter defining ability of material to store charge. The dielectric constant defines that how much charge a material can store. The K value of silicon dioxide is 3.9, and since silicon technology is all about silicon dioxide, here in this system we considered silicon dioxide and its value as the reference. So 3.9 is the reference value of dielectric constant in silicon technology. So dielectrics with K greater than 3.9 is referred as High-K, and dielectrics with K less than 3.9 are defined as Low-K dielectric. In state-of-art VLSI technology, both high and low-K dielectrics are needed and used for different reasons. So their reasons are different, although they are needed. Need for High-K dielectric. Silicon dioxide has been used as gate oxide material for decades. The thickness of silicon dioxide gate dielectric has steadily decreased to increase the gate capacity, drive current, and raising device performance. As the thickness scaled below 2 nanometer, leakage current due to tunneling increases drastically, leading to high power consumption and reduced device reliability. Following Moore's law leads to downscaling of device dimension. Not only length but also the thickness of oxide layer also simultaneously decreased over decades, and now it has become almost a few nanometers. A very small voltage can create a huge field. At this situation with high field, tunneling occurs. Tunneling is basically a quantum mechanical process to describe the conduction in such situation. So tunneling increases and lead to high power consumption and reduced device reliability. Not only that, it may lead to oxide or dielectric breakdown. Dielectric is there to create a parallel plate capacitor. Ideally, there should not be any kind of current conduction. Use of High-K dielectric instead of silicon dioxide leads to increased gate capacitance while keeping gate oxide thickness fair enough so that leakage effects are reduced. K value is higher, so to get the same amount of charge, and we do not need to make this High-K dielectric so thin. So the rising of tunneling can be avoided. Now, need for Low-K dielectric. In digital circuits, insulating dielectrics separate the conducting parts where interconnects and transistor from one another. We have seen that in interconnect series, right? The dielectrics separate the conducting parts. It's not that all the conductors are there hanging in air. No, they are separated by dielectrics. So as components have scaled and transistor have gotten close together, their insulating dielectric have thinned to the point where charge buildup and crosstalk adversely affect the performance of the device. To reduce parasitic capacitance, Low-K dielectric is used instead of silicon dioxide. Here, the Low-K dielectric is used so that coupling between interconnects is minimized. We use that as insulator, and the High-K dielectric is used as gate dielectric in MOSFET. So we are done with this slide. Now let's move to the next slide. Why High-K dielectric? This is a basic MOSFET structure, and here it's gate and silicon in between the gate structure. Now, over last few decades, scaling of MOSFET dimension has been viewed as an effective approach to enhance transistor performance as predicted by Moore's law. We have already mentioned that. Scaling includes gate oxide thickness reduction. So, the gate dielectric thickness is also reduced. Now, reduction in the thickness of silicon dioxide gate dielectric has enabled increased number of transistor per chip with enhanced circuit functionality and performance at low cost. The effective area of one device is basically reducing, and this length is also decreasing. The number of transistor per chip is increasing. As we approach sub 45 nanometer node, the effective oxide thickness EOT of the traditional silicon dioxide dielectrics are required to be smaller than 1 nanometer, which is approximately 3 monolayers and close to the physical limit. Now, such thin layer of silicon is prone to high gate leakage current due to the obvious quantum tunneling effect at this scale. Here is a comparative study. For same current density, this is the silicon dioxide thickness and this is the high-K oxide thickness. In silicon dioxide, tunneling is happening. In high-K dielectric, it's not happening. To continue the downward scaling, dielectrics with higher dielectric constant are being suggested as a solution to achieve the same transistor performance while maintaining a relatively thick physical thickness. This is the reason why we are moving to high-K dielectric. Gate oxide thickness is higher, although the performance is same. We are done with this slide. Let's move to the next slide. Now, dielectric conductance and breakdown. Oxide means an insulator, a dielectric. So, and it's expected that zero conductance through it. Although it doesn't happen, tunneling happening means some level of current is flowing. So, what actually the physics behind it? Let's try to understand. So, we can understand the requirement of a good high-K dielectric. So, this is the metal oxide semiconductor structure. That is aluminum, that is metal here. Here oxide. Here ZrO2 that is basically high-K dielectric. So, let's understand what actually happening here. Performance of MOS devices depends on breakdown properties and the current transport behavior of the gate dielectric. This is the central part of a MOSFET, and here we actually add that source and drain. What actually we do, we apply a gate voltage here. It's grounded. This is a metal plate and this is another conductor. This is insulator. So free electrons are gathered here. So basically a channel is getting formed. When a channel is formed, electron concentration in this zone is much higher compared to this zone because all free electrons has moved to this one. When voltage applied in this gate compared to the ground, here electron concentration increases, high electron concentration. It also behaves like a conducting plate. So between these two conducting plate, it's an oxide. That is the thing. It will work best when there would be no zero current through this oxide. Once this channel is formed, we give set of voltage between the source and drain so that it's a continuous conducting path. Electron flows from here to there. Ideally, in a MOS structure, the conduction of dielectric is assumed as zero. However, in real world situation under high electric field or temperature, there is some carrier conduction because at high field, high electric field, there is some carrier conduction. Tunneling is the conduction mechanism in insulator. In insulator, tunneling happens, and tunneling is a quantum mechanical phenomena in which electron wave function can penetrate a potential barrier. Now, there are 4 different mechanisms in dielectric conductance. There are 4 different mechanisms: direct tunneling, FN tunneling, Schottky emission, and Pule-Frankel emission. Now, this is aluminum. Aluminum side, it's a metal. Free electrons are there. It's an insulator. Although in an insulator, there are some defects and there are trapped, the energy states are there. And if these energy state under high voltage or field, if these energy states become more continuous, a path is there. In direct tunneling, from here, it's covering all the thickness and it's tunneling through like this. In FN tunneling, look, it will come from here to there. It's not the total barrier. It's a partial it's covering. It's partial. Schottky emission is that if there are some energy states are there, so it will cross this barrier. That is Schottky emission. Will come here, from there it will move to this side. Trap assisted tunneling or Pule-Frankel. Electrons through defect states, it's moving from this side to that side. So current is flowing. Under large bias, tunneling current flows through dielectric. Now, when energetic carriers move through the insulator, defects are generated randomly in the bulk of the dielectric film. So energetic carrier, high electric field, a free carrier is there. It got energy. It's moving with high energy. It's colliding, and more defects are getting generated randomly in the bulk of the dielectric film. If number of defects are high enough to form a continuous path connecting to the gate to the semiconductor, a conduction path is created and dielectric breakdown occurs. Such a path. Continuous path is formed between metal and semiconductor through oxide. Current will flow from here according to energy band alignment and how much field is there, which material is there. All these happen, 1 or 2 may happen. Now we are done with this slide. Now let's move to the next slide. Essential qualities of High-K dielectric. Slide 1. Now let's understand what are the essential qualities the High-K dielectric must have so that we can use it and get benefit. K value, band gap and band offset. To get high capacitance, K value must be over 12, preferably 25 to 30. High-K value means the dielectrics will have a reasonable physical thickness to prevent gate leakage. The layer must not be too thick to hamper physical scaling when achieving the target effective oxide thickness. Like not too thin, not too thick also. On the other hand, a very large K value is undesirable in CMOS design because they cause unfavorable large fringing field. K means how much charge it can store. A very high K means can create a high field. Unfavorable large fringing fields can hamper the action of source and drain region. If a High-K dielectric can replace silicon dioxide, the dielectric thickness increases proportionally to keep the same dielectric capacitance. A figure of merit to judge a High-K dielectric layer is equivalent oxide thickness defined as EOT. This is basically a figure of merit. How it's calculated? Epsilon 1 by epsilon 2 into T, where epsilon 1 is 3.9, epsilon 2 is K value of High-K material and T is High-K dielectric thickness. We put epsilon 1 and epsilon 2 and we can calculate T from there. Now thermal stability. All the devices are fabricated at high temperature. Once oxide is done, then metal layer, then interconnect layer, then so many layers are there. Even after fabrication, it must withstand high temperature because rest of the steps are there to occur. Thermal stability in present CMOS processes, the gate stacks must undergo rapid thermal annealing. This requires that the gate oxide must be thermally and chemically stable, especially with the contacting materials. Additionally, oxide should not react with water. Among many High-K dielectrics, hafnium oxide has both a High-K value as well as chemical stability with water and silicon. With crystallization temperature, amorphous materials are preferred to crystalline one owing to absence of grains and good diffusion barrier properties. The grains present in the crystalline system can often be pathways for dopant diffusion and breakdown. Unlike silicon dioxide, High-K oxide usually have low crystalline temperature and can easily crystallize when subject to RTA, that is rapid thermal annealing. If the crystalline temperature for a material is low, then within the process also it can crystallize. In particular, hafnium oxide and ZrO2 zirconium dioxide crystallize at much lower temperature, almost at 400 degrees centigrade and 300 degrees centigrade respectively. According to the above factors, the approach to improve the crystallization temperature of hafnium oxide and zirconium oxide should be considered. The crystallized hafnium oxide has much lower leakage current. Now we are done with this slide. Now let's move to the next slide. Essential qualities of High-K dielectric. This is the second slide. Now, interface quality. The interface between High-K dielectrics and silicon substrate must have the highest electrical quality and flatness. Absence of interface defects and low interface state density DIT. Bad interface quality can cause high fixed charge density, inducing a large shift of flat band voltage, which severely reduces performance and reliability of transistors. So, we need interface between High-K dielectric and silicon substrate. There should not be many interface defects. Otherwise, it will lead to degraded performance and reliability issue will arise. O2 and dopant diffusion through grain boundary. Compatibility with gate electrode. Oxide must be compatible with the metal also. Density of interface states comparable to silicon dioxide. Silicon dioxide and silicon interface is really good one example. We must have a new system where new oxide and silicon interface is comparable to that level. Low lattice mismatch and similar thermal expansion coefficient with silicon. Lattice mismatch, the lattice structure mismatch should not be very high. Mobility compared to silicon dioxide. So these are basically properties we want in our High-K material. Now we are done with this slide. Let's move to the next slide. High-K metal gate. To continue, the downscaling dielectrics with higher dielectric constant are being suggested. Many candidates of possible High-K dielectrics have been suggested to replace silicon dioxide, and they include nitrided silicon dioxide, hafnium-based oxide, zirconium-based oxide. Different candidates are there. Hafnium-based oxides have been recently highlighted as the most suitable dielectric materials because of their comprehensive performance, and they have been included basically. One of the key issues regarding new gate dielectric is the the low crystallization temperature. Due to this reason, it's difficult to integrate them into traditional CMOS processes. If their crystalline temperature is quite low, within the process it can get crystallized. To solve this problem, additional elements such as nitrogen, silicon, aluminum have been incorporated into high-K gate dielectrics, especially hafnium-based oxide. Introduction of new material is also there. New material has been incorporated to increase the temperature. For the gate electrode, both polysilicon and different metals have been investigated along with high-K dielectric. The combination of high-K dielectric and polysilicon gate is not suitable for high-performance logic applications since the resulting high-K polysilicon transistor have high threshold voltages and degraded channel mobility and hence poor drive current performance. Polysilicon gate and high-K dielectric, the performance is degraded, so that's not a preferred combination. It has been proposed that high threshold voltage is caused by Fermi level pinning at the polysilicon high-K dielectric interface, and that Fermi level pinning is most likely caused by defect formation at the interface. It has been demonstrated both experimentally and theoretically that surface phonon scattering in high-K dielectric is the primary cause of channel mobility degradation. Significantly, metal gate electrodes are effective for screening phonon scattering in the high-K dielectric from coupling to channel when under inversion condition. This results in improved channel mobility. Polysilicon high-K dielectric interface, it's not really good for performance. If we replace polysilicon with metal, it gives better results. So we have moved to that high-K dielectric metal combination. We are done with today's episode. Thank you for watching up to this point. If you have a question or query, please put it as a comment. If you have any dislike, also put it as a comment. Don't forget to like, share and subscribe. Thank you again and bye for today.